Think about the microwave sitting in your kitchen right now. You press a button, wait 60 seconds, and your ice-cold pizza is suddenly molten hot. There is no fire, there are no glowing red heating elements, just a quiet hum. Behind that glass door is a localized application of quantum mechanics, electromagnetism, and World War II radar technology. The origin of this technology starts in 1945 with an engineer named Percy Spencer. He was working for the defense contractor Raytheon, testing a piece of military vacuum tube equipment called a cavity magnetron. While standing in front of an active, high-powered radar set, Spencer noticed something strange. A peanut cluster candy bar in his pocket was melting. Curious, he exposed popcorn kernels to the magnetron, which promptly popped. By 1947, Raytheon had industrialized Spencer's discovery into the first commercial microwave, dubbed the radar range. It was a 1.8-meter-tall behemoth that required an active plumbing connection to pump cold water through the system just to keep the internal components from melting. It cost the modern equivalent of $70,000. To really understand how this technology operates on your countertop today, we have to look past the white plastic casing and examine the raw data, the mathematical formulas, and the highly energetic physics hiding right behind the glass door. This schematic shows a vacuum tube called a cavity magnetron. This is the core engine generating the heat. Inside, there is a central heated cathode surrounded by a solid copper block called the anode, which has precisely machined resonant cavities cut into it. A high DC voltage is applied between the cathode and the anode. When electrons are emitted from that heated center, their natural path is to fly straight outward to the copper. But simultaneously, permanent magnets generate a strong magnetic field running straight down through the vacuum chamber. According to the Lorentz force law, this interaction of electric and magnetic fields forces the electrons off their straight path. They are pushed into a cycloidal, spiraling path, spinning outward toward the copper block. As these electrons sweep past the openings of those machined cavities, they induce highly unstable, oscillating radio frequency currents, exactly at 2.45 GHz. This strictly controlled continuous electron spin is what converts standard wall electricity into a directed stream of weapon-grade electromagnetic energy. That high-power electromagnetic energy is channeled through a tuned metal pipe called a waveguide, flooding directly into the cooking chamber. Many people assume that 2.45 GHz is the exact resonant frequency of water. This is completely false. The actual resonant frequency of water vapor is around 22 GHz. If a microwave actually operated at 22 GHz, the outermost layer of your food would absorb 100% of the energy instantly. The outside would completely burn, and the inside would remain completely frozen solid. Engineers chose 2.45 GHz deliberately because it offers the perfect mathematical balance of energy absorption and physical penetration depth. This animation shows a single water molecule reacting to that specific frequency. Water molecules are dipoles, meaning they have a slightly positive charge on the hydrogen side and a slightly negative charge on the oxygen side. When exposed to the alternating electric field of the microwave, these molecules try to align themselves with the field. Because the frequency is 2.45 GHz, the electric field is flipping its polarity 2.45 billion times per second. The water molecules flip continuously to keep up, creating immense molecular friction. We can calculate the exact power dissipation, or the amount of heat generated, within the food using this formula, which factors in the 2.45 GHz frequency, the electric field strength, and the dielectric loss factor of the food itself. The microwave broadcasts an electromagnetic instruction, forcing the water inside the food to generate its own thermal energy through this molecular friction. This specific thermodynamic process reveals another mechanical reality. Physics strictly forbids microwaves from cooking food from the inside out. Microwaves attenuate or rapidly lose energy as they travel through a dielectric material. For most high-moisture foods at 2.45 GHz, the wave's power drops to about 37% of its surface value within just 1 to 2 centimeters. This depth is called the penetration depth. The microwaves are strictly targeting the outer centimeter of the food. The colder interior is cooked purely through standard thermal conduction, as the physical heat from those furiously vibrating exterior water molecules transfers inward. This visual shows the cooking cavity acting as a resonator. When the waves bounce off the metal walls, they collide with each other, creating a standing wave pattern. This pattern consists of nodes, which are dead zones with zero amplitude, and antinodes, which are high-energy peaks of maximum amplitude. A 2.45 GHz wave has a wavelength of about 12.2 centimeters. Because of the geometry of a standing wave, the distance between these high-energy hotspots is exactly half the wavelength. That means the boiling hotspots are permanently fixed exactly 6.1 centimeters apart. If you place a static object inside this electromagnetic field, it will melt aggressively at the peaks and remain completely cold at the flat spots. This invisible grid of mathematical dead zones is the exact physical reason your microwave requires a rotating turntable. When we pull back and look at the fully assembled microwave sitting on a countertop, the appliance operates exactly as the physics dictate. This machine harnesses crossed-field vacuum tubes and Lorentz forces to generate directed, non-ionizing radiation. It utilizes dielectric loss, turning 2.45 billion electrical oscillations a second into perfectly calibrated molecular friction. This machine functions as a high-precision thermodynamic engine, successfully miniaturizing complex, large-scale military technology into a standard, modern household tool. If you found this deep dive into the math and mechanics of the microwave fascinating, hit the like button and subscribe for more data-driven breakdowns of everyday engineering. Let me know in the comments, what technology should we tear apart and analyze next? Thanks for watching, and I'll see you in the next one.